Good morning, everybody. This is Ørjan Nottveit from Radiocrafts, and I would like to welcome you to this webinar on how to connect hundreds of wireless IoT nodes to one gateway. So this is about scalability of wireless sensor networks. So now we are 1 minute past, and I think it's on my counter of the people who are listening in, it is pretty stable. So it seems that everybody which is here is already signed in. So we will just get started. Just to present myself, my name is Ørjan Nottveit. I'm the R&D Director at Radiocrafts. This webinar is scheduled to last for 30 minutes with a 10 to 15 minutes Q&A session afterwards. You can introduce yourself in the chat window. That's just good for us to see who's listening in. Also, you can post questions in the chat window while I go along, and we will take them at the end of in the Q&A session at the end. And we will also post a recorded version of this webinar on our website, so that in case you have colleagues who want to listen, look at it, or you want to, or for some reason you want to look at it again. So to get started, when you design a wireless sensor networks, and I've been working with a lot of different customers on a lot of different cases on this, it's very important that you start with a system design and a top-down approach. You have to consider what is that you want to monitor wirelessly. It might be very many different use cases of what you want to monitor, and then you have to consider what is the acceptable sample rate when I want to sample something wirelessly. Also, do you want to control something? That means, do you also want to use a downlink to adjust things wirelessly, or are you just gathering data? Do you need to have several sources and do correlation between data? For instance, in a predictive maintenance application, you might want to handle several parameters like heat and vibration in a machine to do some correlation at the back end. What type of data you need? Do you need a lot of data to do like artificial intelligence in the back end, or are you kind of basically just want to know the temperature in the room? Then you don't need a lot of intelligence. When you start this top-down design, you will have some outcome of your, let's just say, system design. You will have a node density outcome. How many nodes will you have wireless nodes will you have in an area? How often will the different nodes send data? Some might send every 5 seconds. Some might send every 12 hours. So it's a very different scenario depending on your system. Packet success rate is also important. What is the required packet success rate for your applications? So I'll talk a bit more about these elements further down. An important part of this top-down approach is to consider things as a control system. That means that we want to monitor some data wirelessly. We will kind of sample them in a certain sample rate. And you can imagine global heating. If you want to have a wireless network covering the entire Earth and measuring global heating, it's kind of a slow process. It takes years for it to change a couple of degrees. So you don't need to update that every 2 seconds or 1 second. If you, on the other hand, monitor the used parking spaces in a garage, that can change. 5 seconds later, there could be one parking space which was open is then filled, and another one is open 5 seconds later. So you need to make sure to kind of sample those processes quite much more often. And that's in a control system. That sample rate also gives you how quickly you can control a system. So basically, when you get some data, you want to adjust something. That's the basis of a control system. So the point with this is that you need to decide in your system what is the business, what is the process you're trying to control, and what are the speed of it, how it varies. Here I'm just showing a graph and some sample periods, and that shows that if the sample period is too far between the times you get wireless readings from a sensor, you will lose some information. You will lose the top in the middle if you sample too slow. Also, one of the big trends these days is, of course, AI and artificial intelligence. And it comes from the trend which was like 5 years ago, which was the big data trend. And what we see, there's a lot of businesses trying to do intelligence based on a lot of data processing. And this just requires more data, because if you read one temperature in a room every 12 hours, there's not a lot of intelligence you can gather from that. You need to have more data, and you have to have data from multiple sources if you want to do generate some value for the end customer. So if you want to monitor a room and you also want to monitor the people coming in and out of the room, and you want to correlate them together with the HVAC systems, then you can start to optimize it and save, for instance, energy by reducing the room temperatures. Historically, we see that the request for more data is increasing. It's not just when you have the kids at home with their iPads streaming video, but also in the industry. It's about getting more and more data, which is the trend all along. And also we see that the IP as network layer is coming more and more into the wireless sensor networks as well. And there's more and more requirement on security. And all these parameters makes the increase for more data and more bandwidth in your wireless sensor network. Then that leads to a very strange curve here, which just basically shows that how the technology trends are going, that everything we have has more and more processing power. We have more and more storing capability in our devices, in our backend systems everywhere. And in the backend, the data rate is going, the data rates in the Ethernets and the fiber networks are going up all the time. And the wireless sensor network data throughput has also gone up for many years until it suddenly has dropped down. So that means that when we were doing 50 and 100 kilobit a couple of years ago, the trend now is that people are going to 100 bit per second type of applications, which is quite a contradiction when you look at the requirements on the earlier slides. When you design a system from the top down, you also have to consider what is the required packet success rate for your application. Because in all radio and wireless communication, there will be packet loss. But at some point, the packet loss becomes a problem for you. That means that you cannot really trust your data anymore because you don't know if it's updated. And that means you cannot really make any business value based on the data. So I mentioned this, the parking area occupancy sensors. If you have a parking area and you have wireless monitoring of the different available parking spots, if the end customers with the cars continues or a lot of the time notice that the information is wrong, they will stop trusting the system, they will complain, and the business value of the entire system is flawed. Also, if you have like a service queue monitoring, that means you're monitoring how large the queue is. So you opened another counter if it's a long queue, and if there's no queue, you will shut down a counter to try to save money and optimize. If the system is not giving you correct data, you will do the wrong business decisions all the time. Also, air quality monitoring. If your room is getting hot and a lot of moisture in it and a lot of VOC gases, and your system isn't reporting correct, and you're not turning up the ventilation, the system is flawed. So we see that in many cases you will expect between 99 to 99.9% success rate in order to have a good system. There could be cases where you require 99.99 as well, I would imagine. And there are some cases where you say 60-70% accuracy is enough. It all depends on how your system looks like. Here we have some examples of systems. Process control, for instance, in a factory, it might require update rates of seconds or even milliseconds sometimes, and you need very high reliability. Monitoring temperature and humidity in a paste printing machine, which now is an example we have worked in, is that you want to monitor every 5 minutes or something, which requires less update rate, but you still would like a probability of success of like 99%. Building management system, queue monitoring. Then you have agriculture, which is soil moisture, for instance, which are very slow processes. So if it is wet in the morning and you don't have to measure it 10 seconds after, it's still wet outside. So then I completed a bit on the top-down design. Then I'm going to talk a bit about the challenges you get for the different, if you have a high density network with high update rates. So one of the major problems you will end up with is congestion. So you need to do an analysis on your system with regard to congestion. So for us, congestion is when there are so many devices sending so many packets on the same channel that they interfere, and the packet error rate significantly increases compared to like a single sensor network. We have chosen to define congestion with packet loss increased by 1%. We see others use 10% as a measurement, but for us, that's if you have 10% packet error rate, for us, that's not a very good network. We have our new wireless solutions, which is called Riot, where we have analyzed congestions. We have a test system of 28 nodes during the Riot 50 kilobit per second mode. This is a long-range radio, which uses also listen before talk and retransmission. And we have tuned them to send every data every 4 seconds. And we send 7 of the devices to pull data, so that means they're sleeping and they're getting a downlink channels as well every 10 seconds. On such a network, we also did it on 10 seconds and 30 seconds and longer, of course. But at 4 seconds, we still have a packet success rate of 99.93% when we run this over 3 days. So this is the network we're running without any congestion. Because the congestion is basically based on the data packets, we can take that network and do equivalent networks. So that means that the equivalent network would be 100 nodes, which sending every 15 seconds. That would be no congestions. We also could do 1,000 nodes, sending every 3 minutes, which will give the same amount of traffic, meaning no congestion. We could also do 7 nodes, 1 second, sending data every 1 second. So that's a very quick network, but you see we are reducing the number of nodes for that network in order to avoid congestions. We also have this 5 kilobit mode in Riot, which is more like a large area network, where we also see we can do 100 nodes and sending data from the sensors every 3 minutes without congestions. So this is how we see the Riot network performing in a high node count and high update rate type of scenario. If you compare it to alternative technologies, we could look at LoRaWAN, for instance, which is a very popular technology. We have some curves coming afterwards as well. But basically, they end up with, if you want to use a LoRaWAN setting, a standard LoRaWAN setting of spreading factor 12 in 125 kilohertz channel, and sending 20 bytes every 16 minutes, they get a success rate of 90% with 120 nodes. So what does that mean? So first of all, 90% is, for our case, not a very good network. So it is, but if that's acceptable for your solution, that will be very, very good. And they're also sending every 16.7 minutes. So that means they're not sending in a very high, with high update rates. I think it's better to show this curve, which is basically the curve which these statements are taken from, and they also have a link up from to the paper underneath. So it's a bit small figure, but what you will see on the right side is that if you have the number of nodes and you have a success rate on the left, and it is this SN3, which is the typical LoRaWAN connections, and you see that you have very few nodes before this success rate at the left goes below 99%. Let's talk about a couple of nodes actually before you start getting that challenge. This is taken from a different paper, and it also shows the number of transmitters per gateway in a LoRaWAN with spreading factor 12 in this case. And we see that the percentage packet loss is showing here. And you see that if you have 100 nodes, you see that the green one, which is the percentage packet loss, is going up to 50% at 100 devices. So again, going for 1% packet loss, you basically end up with basically a couple of devices. What you also see from this is that you get the throughput on the right with the purple lines, showing that if you have 100 devices, the throughputs you can actually send per hour per device is based on regulation 10 packets. So again, very slow update rates, and of these 10 packets, actually 5 will get through. You can do the same with LoRaWAN with the spreading factor 7, which is a different mode in LoRaWAN, which is a bit higher data rate. So it's not that extreme range anymore, but it's more, let's say, it's more comparable to our 5 kilobit mode. You see that with 100 devices, you still have and they're all sending this 200 frames per hour. Then you see you still end up with 50% packet loss at 100 with 100 devices. So congestion is one part of the equation. Battery lifetime is a second part of the equation. All these LPWAN technologies, LoRaWAN, Sigfox, wireless Membus 169, they all have a long range, but they all transmit much more energy per data transmissions. So this is a comparison here showing several different technologies. And if you look at the column 3, which is energy per transmissions, you see that the LPWAN technologies, LoRaWAN, Sigfox, and wireless MBus and 169 have very big numbers of the energy per transmissions. So it means none of these technologies are revolutionizing in terms of technology. Basically, they all use more energy to send the same amount of bits or bytes. And you see that the Riot at 50 kilobit and 5 kilobit are quite different technologies. And they are not aimed at the same range. So that means that they're not aimed at this many kilometer range in an urban environment. They are intended for a bit shorter range, but they are intended to support more devices with higher update rates. So the interesting part is also the consequence of this energy transmission, energy used per packets in the red frames, where you see with a 500 milliamps coin cell batteries, these LPWAN technologies will last 4 to 8 days. Then you have to change the batteries. So that means if you're sending, and this is based on sending every 15 seconds data. Again, if you're sending every 24 hours, it's okay. They probably can have a long lifetime. But if you're sending with high update rates from your sensors, these technologies are not suited. You also have the same numbers on the right with a much larger battery. It's a AA lithium battery with 2,400 milliamp hours. And you see that they will then last like 17 to 38 days before you have to change this battery. And that's a pretty expensive battery. And you see that with Riot 50 kilobit, we end up with 12,000 days, which is quite a few years actually. So for me, it's a clear difference between the LPWAN technologies, which are made for very slow data transmissions and a very long time between each. And they're not made for high update rates like 15 seconds or even close to 15 seconds. So that means that if you have wireless sensor networks where you need high update rate on the data reading, you need other solutions. The third problem when you want to have many devices in one gateway or one coordinator is the regulations, and that is both the operator regulations and it is the like CE and FCC regulations. We know that Sigfox is limited to 144 packets per day. That means 6 packets per hour. That's based on what the operator says. And in addition, due to the CE regulation, you can only send packets every 2.5 minutes also. But here you see the operating regulation is the most strict. LoRaWAN, if you again use this 300 bit per second mode, LoRaWAN operates in different bands in Europe. Some are allowed to send 1% and some are allowed to send 0.1%. So this will give you different requirements to how often you can send. If you are in the 1% band, you could send every 2.25 minutes as well. And if you are in the 0.1% bands, you have to wait 22 minutes between each packet in order to fulfill regulation. An interesting note here as well is that if you consider the gateway, this is also why the gateway in either Sigfox or LoRaWAN will not be able to acknowledge all packets. Because if you have 100 nodes sending every 3 minutes, the gateway would then be sending 300 times or 100 times in that same period, and the gateway will violate CE regulation. So this is also why none of these technologies, they both offer two-way communication, but the operator will not be able to use it because of regulation. So it is a feature which is kind of more for the marketing side than a real operating scenario. Again, if you have a your own LoRa network and you have 3 devices, that's fine. You can do two-way communication, but in a large LoRaWAN network or a public one, you will not be able to do two-way communication. So let me give you an example of a use case. Assume you're having a factory or a large property, which is 10,000 square meter. And this is in a IoT enabled factory or property. So that means that in average, every 10 meters, there's a sensor of some type, monitoring a machine, monitoring a room usage, monitoring some humidity, monitoring some gases, and anything. Imagine these sensors send 20 bytes every 3 minutes, which is it's okay if you want to monitor an office building, for instance. You want to monitor if there's if a room is in usage. Maybe 3 minutes is and monitor some temperature in a room. Maybe 3 minutes is an okay scenario. That means if you want to monitor this network with a LoRaWAN using spreading factor 12, which is the longest range, then you end up with a success rate, and this is based on the curve I showed you earlier, of 60 to 70%. In addition, you will be violating regulation rules, so you're basically not allowed to do it. And one AA battery will last you for 300 days. If you use the same example and use the Riot 5 kilobit per second, you will have a success rate based on our measurements here of 99.93%. It will be a CE-approved solution, and one AA battery would theoretically last 42 years. The reason I'm using theoretically is that the battery itself will probably die after 20 years. So 42 is a bit theoretically, but it means that it will take a very long time before you change that battery. So this is for me a good summary. So the purpose of this is not to say that LPWAN technologies are bad. They are at no point bad. They are very good technologies for their applications. So that means that if you have low data rates, so there's a low amount of data coming, you basically want to transfer a bit, like an on or off state of something. Maybe then they're good. If you want to go up with data rate, so that means you want to go to the right at this figure, you need to consider other technologies because the LPWAN technologies will soon have a limitation. Also at the left, you see 3 different parameters. You see the node density and the update rates. So that means that if you have a high density of nodes and you have high update rates, the LPWAN technologies like LoRaWAN and Sigfox will not do the trick for you. You need other technologies. Also, if you want to consider low power devices, which means that you want to be battery operated with a small battery and should last for a very long time, you also need to go up to get the low battery. On the right, you will see that BLE is obviously a very good solution for the very short range. So that means if you are considering covering a room of 5 times 5 meters, that you want to do some sensors in that room only, I would obviously say that BLE is a very good solution because it's very power efficient. You get high data rates, update rates, and very low power consumption. In case you want to do a factory, like 10,000 square meter factory, and do quite much data from those to do to monitor your factory, to do in order to do the right business decisions for your factory, then I think you're in the green area. And if you're covering a large city and you want to monitor like position of garbage bins, which you want to update every 1 hour just to know where they are, I think obviously you will have to go with some of the LPWAN technologies like LoRaWAN or Sigfox. So all of these technologies have their benefits, but you have to adapt your solution to the requirements in your application. So to summarize, due to congestions, due to battery lifetime, and due to regulations, LPWAN technologies are suitable for update rates of 50 minutes and above. That's basically what the studies show and what the regulations show. If you have very high density network, like 100 nodes connecting to one gateway, you probably want to go up to update rates above or up to 1 hour or above if you want to have a reliable network. If you have if you need a wireless sensor network with many nodes and high update rates, Riot is obviously a much better solution. And then you end up with different application this is suited for. So again, LPWAN, if you want to do water metering, for instance, 169 MHz wireless M-Bus, very much used for water metering, which you do 5 to 15 readings per day and covering a very large area. Obviously, LPWAN is the solution, way to go. If you do soil moisture sensors with reading the soil moisture every hour, that's also LPWAN. The challenge there is if you want to control like irrigation systems at the same time, you need two-way communication. So that means some of the LPWAN technologies will actually not do the trick, as they really do not support two-way communication. City air pollution, monitoring every 1 hour or something, which also would be a very good solution application for LPWAN. If you just want to send data when something has happened, like an alarm, or just that now this door has been opened, or no, which is also very rare events, but you want to send just on the events, you can also do it with LPWANs. However, if you have, you might not get acknowledged because they don't support two-way. So with Riot, you have other type of applications which suits better. That means facility management of a property. You have service monitoring, building management, parking occupancy sensors, machine learning or AI, where you want to do, you need more data in order to do back-end artificial intelligence, for instance, for predictive maintenance. Also, if you want to have control systems where you need an active downlink to control something, you would like to use Riot. So that is basically the end of this webinar. So if you have any questions, I saw there was some had some challenges with the to get the webinar running, but hopefully that has been sorted out. So if you have any questions, you are free to put it on the chat window. So the purpose of this webinar is, again, not trying to say that some technologies are bad and some technologies are good. Obviously, there is a lot of good in all of these technologies, but there's not one solution that will fit all applications, and that is one of the main messages. And the other one is that if you then want high density network with high update rates and even low power consumptions, then LPWAN is not the right way to go. And we see a lot of customer where they first chose the technology based on that sounds like a good technology, and then they start to analyze the use case afterwards, and then they end up with, okay, this doesn't really match. And if your project is then far down the line, then it will be very expensive to change. What's the possibility of realizing multi-hop network with LPWAN? Yeah, I'm not sure what you think about when you say LPWAN here. I know there has been some studies in doing multi-hop with the LoRa. That will not be LoRaWAN, but LoRa. Also, you can do multi-hop like repeaters with 169 megahertz. When you do repeaters, basically each packet is sent more times, so you will end up more quickly in a congestion scenario as well. We are also we'll be launching soon a multi-hop network using a like 50 kilobit. It will not be Riot, but it will be a similar technology. but it will include multi-hop or mesh capabilities, which will then be able to get the same coverage as you will get the same coverage as LPWAN technologies. But the advantage of using mesh is that each end node will have a very short distance to its parent, and thereby giving the end node very low power consumption. You can realize multi-hop network with LPWAN technologies, but the purpose of LPWAN is to not use multi-hop, to put it that way. The purpose of LPWAN is to avoid the mesh and avoid the routers. I hope that answers your question, Narjana. And I don't see any more questions. So in that case, I would recommend that you can go into our webpage, and there you will find more information about Riot at this webpage. You will also be able to find it if you just go to radiocrafts.com, and feel free to check it out there. And if you have any more questions later, you can contact us through our website and our contact form there. So I hope you enjoyed this webinar, and I hope I was able to clarify some of the challenges you have with LPWAN technologies, and how other technologies might be better for some applications, while LPWAN is fantastic for others. Okay, thank you very much.